Hello everyone, today we're going to look at a proof by induction problem from IB Maths Higher Level. This is an AA problem and we're just going to go right into it. I've not seen this before, so we're going to kind of work through the problem together and see if we can get to the answer. So we're told here that we need to let R be a real number, that's what the R represents, that does not equal 1. Using a method of mathematical induction, prove that 1 plus R squared plus R squared all the way up to Rn is going to be equivalent to this setup. And this, looks to me a lot like our sum in a geometric sequence setup, right? A times 1 minus R to the n over 1 minus R. I don't know if we're necessarily supposed to use that formula when we're solving this problem, but that's what this reminds me of. And we're also supposed to do this for all values n to the power. N is sort of a positive integer in this case. Okay, so this is induction. We're going to state some assumptions to begin with, but we might need to add on some assumptions later on. So I'm just going to say let R be a real number, not an integer, a real number. R is not going to equal 1. N is going to be a positive integer. So those are just the assumptions that they've basically stated here. And then we'll use those. We may add on to those later if we need to introduce other assumptions, but we have to state those. And this is the relationship that we're looking at. Since this is a mathematical induction problem, we basically break this down into 3 steps. And the first step is going to be to look at a base case. So we're looking at the first value for n that we are interested in, which for us, n is a positive integer. I'm going to start with n equals 1. So we're going to go let n equal 1. And when n equals 1, we're going for basically 1 plus r as the left-hand side, right? Because that's the setup here. This should be equivalent to 1 minus r to the power of 1 plus 1 over 1 minus r. So how can we get to this position? Well, I'm going to adjust the left-hand side until we get there. It looks to me like this is going to be 1 minus r squared, and I can see this as a difference of 2 squares. So I can represent the top of the fraction as 1 plus r, 1 minus r, with a base of 1 minus r. And then this would turn into 1 minus r squared over 1 minus r, which is in fact equivalent to this. So we've demonstrated at this point that our relationship is at least true for this very first value of n, which is going to sort of set up the chain that we're proving with the induction method. Because what we're basically doing with induction is we're going to demonstrate that it's true in this first case, and then we're going to demonstrate that that if it's true in a particular case, it has to be true in the subsequent case. So for example, we're going to connect them sequentially. We're going to start with saying that we're going to make an inductive assumption, right? So we're going to assume that when n equals k, that this by definition will be true, so that we are going to go 1 plus r squared all the way up to rk. This will have to therefore be equivalent to 1 minus rk plus 1 over 1 minus r, by definition. So we're not actually proving anything in this step. We're setting up an assumption. But the way this is going to work is we're going to connect our assumption to an inductive step, which is the next and third part. So the inductive step is to let n equal k plus 1. And here we assumed that this was true. And the idea here is if it's true for k, and we can then demonstrate that it would follow that it's true for k plus 1, we've basically created a link where, provided I know the previous n value is correct, the subsequent n value must also be correct. And the reason that's going to help us demonstrate the proof is we've already established that our first value for n, 1, is true. So if we can set up this link, it means by default n equals 2 must be correct, and therefore n equals 3 is correct, therefore n equals 4, n equals 5, n equals 6 forever. So once we've set up the relationship, we can then use the relationship later on. I'm just going to grab the problem and drag it down so that we've got it to look at, because I don't want to have to keep scrolling. So this is going to go here. But we're going to definitely use the assumption that we have. One of the things I'm looking out for when we're doing the inductive step is an opportunity to use this somewhere. So that's kind of a guiding principle that's going to help us get through to our end result. What we're trying to prove is that 1 plus r squared dot 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 rk plus rk plus 1, right? Because that's now our final term. We're trying to prove that this is equivalent to 1 minus r k plus 1 over 1 minus r. Hang on, was it n? Have I just immediately done this incorrectly? N plus 1. Yeah, so we need to... no, n plus 1. We're fine. So we were subbing in the k plus 1 for n. Okay, so if we can demonstrate that this is true, using our assumption probably, then we can get to a demonstration that this is correct. So what I'm now going to do is almost immediately I'm noticing that this looks an awful lot like the left-hand side of our inductive step. So that probably is my substitution. So I'm going to use assumption. I'm just going to write down that I'm using it. I'm going to call this assumption 1. So we'll label it here, assume 1. Assumption 1, we're going to replace what we have here with what we found up there. So that was 1 minus r k plus 1 over 1 minus r. And now we still have the rest of this. So we've still got the k plus 1. Always with proofs, I'm modifying this just on one side of the equation. So I'm going to change the left-hand side until it eventually matches up with the right-hand side. So what are we going to need to do now? Well, we've got two separate fractions. I want to get this, or two separate values. I want to get this to look like what we have on the right-hand side. So I am probably going to try and combine them into one fraction, because on the right-hand side, we just have the one fraction. That means we're going to have 1 minus r k plus 1, 1 minus r. And then to make this match up, we're going to have this times 1 minus r over 1 minus r. So with this, we really want to take our time showing our working, because a proof is supposed to be sort of self-evident when you read it. And so you don't want to be skipping too many arithmetic steps, because that's going to kind of throw off what's happening in the proof. So all of this comes together like this, and I can expand these brackets too. Now when we multiply rk plus 1 with minus r, what's happening is I'm basically multiplying by r to the 1 power. And when you multiply two bases together that have different powers but the same base, you're going to add up the powers. So this becomes minus r k plus 2. It's still negative, because a negative value times a positive value is going to end up being negative, right? So that's still, we've still got that component. What I'm noticing here now that we've expanded this is it looks like these terms in the middle are going to cancel each other out, and we're going to be left with 1 minus r to the k plus 2, and then on the bottom we're going to have 1 minus r. Now, here's the question. Is that what we were looking for? Pretty close. I'm just going to make it look exactly the same as what we have over on the right-hand side, which is we have k plus 1 plus 1. So it's a bit pedantic, but just to make sure that we're really driving the point home, k plus 1 plus 1 over 1 minus r, because k plus 2 is the same as this, and therefore we have over here identical values. We've proven our identity. So this is done. Okay. So we've set this up. Just to sort of recap how the proof works, we've established at the beginning with our base case that this works for when n is equal to 1, right? So we were able to just rearrange this and get it to work for n equals 1. We then established if we assume a value of n equals k, we can prove that it will also work for k plus 1, because we're able, just using our assumption, to get the two sides of the equation to match up. That means that so long as the previous term, like an n equals 5, is correct, the subsequent term, like an n equals 6, will also be correct. So you're sort of going out like a sequence from n equals 1, you can then infer that it will be true for n equals 2, and also n equals 3, n equals 4, n equals 5, n equals 6, all the way up to infinity. So we've now proven this in all positive integer cases. What we are going to need to do is establish a conclusion for this. And there's sort of three elements that I want to make sure I'm including in a conclusion to a proof. I'm going to want to, let's just put this in. Is this going to come out as black? I'll change it. So I'm going to want to provide a written explanation, right? So why is this correct? How can we assume that this is correct? I'm doing this in just typing it because there's no way you're going to be able to read my handwriting. So why do we know that this is true? So we've established since, I'm going to label this for my own values. So this is going to be statement A. I would, if I was using a pen, I would probably just write it out again. Right? I would say since statement A is correct, since statement A is an identity with the left-hand side equivalent to the right-hand side, the statement is correct. The original statement, the statement is correct for all n equals k plus 1, provided that n equals k is also correct. Assuming the base case as the base case n equals 1 is correct, the statement will be correct for all. Let's be more specific. So we'll say the sequence 1 plus r squared plus r to the n will be equivalent to, I'm going to write this out with pen, but I'm going to leave a gap and then I'll draw it in for all values of, for all positive integer values of z of n. So what are we establishing in a conclusion to a proof? Well, we need some kind of written explanation for why this is true. And in some proofs, like I think in this proof, it's relatively self-evident from what we have written mathematically that this is correct. Other proofs, you're having to make some kind of inference or observation, or it's not immediately obvious perhaps why what you've written out mathematically is correct, or why it implies that your statement is correct originally. So we need to, in those cases, provide a more robust written explanation. Here, it's a fairly basic explanation, right? I'm just saying, since we were able to get this identity at the bottom, it's true by induction. You can also just write by induction. And then I'm stating what we are establishing to be true. So I'm saying as the base case is correct, the sequence, you could say therefore the sequence, people like when you include therefore, so say therefore the sequence 1 plus r squared all the way up to r to the power of n will be equivalent to 1 minus r n plus 1 over 1 minus r for all positive values, integer values of n. So this is establishing what we're supposed to prove. And you'll also notice I'm making sure that I include the assumptions that we have at the beginning, right? So I'm saying for all positive integer values of n to be specific about when the statement is going to be correct. And again, what I could improve here is probably say that we're going to call this statement B. So statement B is correct, provided this is correct. Therefore, the sequence will be equivalent to all positive integer values of n. So you're looking in your conclusion to have some kind of written explanation of why the proof is correct even if it's really obvious, I'd still include some kind of written explanation. You want to restate what you have proven, and you want to make sure that you're including, gosh, that's a lot of lightning, or thunder rather. You're going to want to make sure that you include in that statement at the end the assumptions that you have set for yourself at the very beginning. And then that's all that you need to be doing for this kind of proof.